Could you please tell us which grades are you in so we can have an idea at which level we should talk? Grade 8, 11, 9, 10, and 9. Okay, great. Yeah, thank you very much. This is fantastic. What we're going to talk about today, having in mind that you haven't looked at the other videos yet, so that we don't make use of anything that was already explained there, we're going to talk about today deductive reasoning. Has anyone heard this term before? Brandon, what's your take on deductive reasoning? How would you describe what is deductive reasoning?
Well, if anyone's a Sherlock Holmes fan, then they might have seen deductive reasoning. But on a more serious note, how do we describe it? It's about drawing conclusions from what you have available in front of you.
It's about drawing conclusions.
Indeed.
Now, let's give an example of drawing a conclusion. We've got here Tim, and Tim went into a room and saw that there was some water on the floor, and he also saw that on the table there is an empty what's the name of this place where fish where you keep fish?
A fish tank, fish bowl.
Fish bowl, yeah. And from what he sees, he draws a conclusion that somebody must have spilled the fish bowl. Somebody must have that the water came from the fish bowl. The water came from the fish bowl. Does everybody agree that this would be a possible conclusion that Tim can draw from what he sees? Now, great. Okay, so it's interesting. Bosiswe, you said that you said no. Would you like to maybe expand on your answer? Why do you think that it's a no? Everybody's saying yes, and you said no. It's very interesting to hear from you why you think it's a no. And also, Mpo, you also said no, and Amantle and a few others also have said no. So, oh, that's very interesting, because the fish bowl is not tilted. So it seems like there isn't enough evidence to know that this water that did come from there. And there's also no crack on the fish bowl. So this is an interesting thought. So do we now say that we cannot draw this conclusion? Those of you who said yes, how would you respond to this? Do you still say yes, or now you've changed your mind? Some of you that have said yes, we can draw this conclusion. Maybe you can justify your answer? So meanwhile, I'm going to write out the lack of evidence here. Fishbowl isn't tilted. No crack on the bowl. Nobody seems to want to justify why yes. Brandon, would you suggest why we could nevertheless draw this conclusion?
Well,
or you also think that there is not enough evidence?
With what our character sees in the room, it doesn't seem to be anywhere else the water has come from, right? We know nothing about the ceiling leaking, or we don't know if anyone else has been in the room. So it seems plausible it must have come from the fishbowl.
There's no other source. That's right. Yeah. So on one hand, we have this one side that's saying there's not enough evidence. Now we also have the other side that says it is plausible because I hope that's the way one spells plausible, because or is it with I? Because there is no other source for water. So basically, we're saying that the fact that the water came from the fish bowl is really a guess. It's not a conclusion, it's a guess. What is the difference between guess and conclusion? Would you like to describe in the chat what do you think is the difference between guess and conclusion? How would you describe, Brendan, what the difference is between guess and conclusion?
I would say that a conclusion relies on available evidence of something, and a guess is based on a gut feeling or a preconception, past experience, perhaps. Although I think a conclusion can be, a guess could be a conclusion, but I think they're a little bit different.
So I think, isn't it kind of in this scenario specifically, we have kind of mixture of both, right? There is this gut feeling because there is no other source of water, but if indeed there was no other source, if we were sure that nothing else happened in this room, nobody came into the room and so on and so forth, we could maybe be more sure that the water could have come from the bowl. So it's a combination of evidence with the gut feeling maybe that we are witnessing here. Let's see what we got in the chat. A guess is a theory. A guess is based on intuition or a hunch, gut feeling. In other words, okay, that's great. There isn't much evidence to support it. Yeah, that's a very good answer, Paul. Well done on that. So when there is, so you can maybe have kind of a scale where you got less or more evidence. So we can draw a scale like this, where this direction is evidence and this direction is just intuition. Now, guess what? When conclusions are drawn anywhere on the scale, anywhere in this place, anywhere here, on this entire big scale, that type of reasoning is not called deductive reasoning. It's called something else. That type of reasoning is called inductive reasoning. As soon as we don't have full evidence, as soon as there is a place to doubt, even if it's a tiny size of a doubt, it's not a deductive reasoning, it's inductive reasoning. Deductive reasoning we are 100% sure of our conclusions. %100% sure that the conclusion is correct. And guess what? This never happens in real life. So in real life, you can only come close to the deductive reasoning. You can never do real deductive reasoning. However, it happens all the time, but not all the time. In fact, some of the times, because inductive reasoning is also useful there. It happens some of the times in the subject called mathematics.
And what happens in a courtroom is a very nice example of inductive reasoning.
Yes.
You don't always have all the details of a case, but you try and argue based on what is available.
Yes. Coming back to this situation, it could have been that Tim's friend, whose name is Tiny Tim. Tiny Tim could have come to the room with some water in a cup, spilled the water, and then set up the room in such a way that Tim would think that it came from the bowl. So it's unlikely, but it's possible. And so in deductive reasoning, we have to be 100% sure. Does that make sense to everyone, or should I re-explain this brief definition of deductive reasoning? But now we're, of course, going to give examples from mathematics. Okay, so there's a request to re-explain. So let's look at an example. X plus 2 equals 5. Can we conclude from this? That x equals 3? What do you think? Okay, I see a few yeses there. Can we be sure that x is 3? Can we be 100% sure that x is 3? Or is it maybe possible that x could be also something else? Now, it turns out that we can be sure indeed, but now, how are we going to prove that we can be sure? We need to demonstrate, if we if we just rely on our feeling that we can be sure, that's not being sure anymore. That's using intuition. It's not evidence anymore, right? So if we are saying that we can be 100% sure, then we have to be able to prove that, like in a court, but this time in such a precise way that there is no doubt that X must be 3. And I see that there are suggestions that we can calculate using the acquired methods. And indeed, we can. There is inverse operation suggested there. So actually, the best way to do this is the following. It will be a bit lengthy than from what you might have seen, but it is much more certain than what you might have seen before. So you begin with x plus 2 equals 5. And now you've got two numbers that are equal to each other. The left-hand side, this one, and that one. If I take two equal quantities and I subtract the same amount from both of them, they will remain equal. Does everybody agree with that? If I subtract the same amount, namely 2, from both quantities, then they will remain equal. Do we agree on that? So do we agree that we can be sure that from this first line, line 1, we can get to line 2? Fantastic. Now, next, we can simplify the left side and the right-hand side of the new equalities we got, right? X plus 2 minus 2, that's the same thing as x. Why is it the same thing as x? Well, we could rewrite this as x plus 2 minus 2. The right-hand side there is going to be 3. We're definitely sure of that. And then 2 minus 2 is 0. So we get x plus 0 on the left side. You see, I'm doing it step by step. And then in the fifth step, x plus 0 is, of course, x. So we get x equals 3. And what is instrumental here is that at each step, I was sure, 100% sure, that I could get the next step. Every time I was 100% sure. And because each time I was 100% sure, when I combine these steps, overall, I can remain to be 100% sure. If at least one of these steps wasn't 100% sure, then the entire conclusion would have not been any more 100% sure. Does this explain better what does it mean to be 100% sure in your conclusion? Fantastic. So this is deductive reasoning when we are 100% sure. That's called deductive reasoning. So let's write this down again. Deductive reasoning is when we draw conclusions in such a way that we are 100% sure in their truthfulness. Now, some people think that mathematics as a subject of study, or maybe as a career, is for people who are good at calculations, or maybe for people who can remember very complicated formulas. The truth actually is that mathematics is for those people who like to be 100% sure, who get upset when they're not sure about something. And as we said, in real life, we can never be 100% sure. So mathematics is a nice, beautiful world you can escape to where you can be, where you can do something that you can't do in real life. But of course, mathematics also has another very important component, which is its applications to real world. when you apply your mathematics to real world, you can never be 100% sure, because your applications depend on your way of interpreting the real life problem in a mathematical language. And that interpretation is never 100% sure. But once you are in the mathematical side, then the conclusions you draw there will be 100%. But then when you apply back, because the first step wasn't 100%, it's not 100% anymore. So let's illustrate this. So you have real life problem. You turn it into mathematical problem. But this process, which is called modeling, is not 100% process. Why not? Because there might be some tiny detail about real life that we might have missed during mathematical modeling. We can never be fully sure we didn't miss anything. And then you solve the mathematical problem. That one you do through deductive reasoning. So there you're 100% sure. And then you apply. You interpret back the solution to the real life. Maybe I should draw an arrow this way. Now the validity of this application depends on the truthfulness of the modeling. So the application will be as true as the modeling was, but because we're not sure exactly how true this one is, we can't be sure of the whole process. And that's still very important. As you know, mathematics has very important applications in real life. So sometimes even in mathematics, we're not 100% sure, but we still are doing important things. By the way, this is where one can start distinguishing between applied mathematics and pure mathematics. So the advantage of applied mathematics over pure mathematics is that in applied mathematics, you get to solve real life problems, which is very exciting. The disadvantage is that it's no longer 100% sure. And the advantage of pure mathematics is that you can be 100% sure. Disadvantage is that before you start applying your pure mathematics, you don't know how to make use of it in real life. So basically, pure mathematics lives at this level here, whereas applied mathematics is concerned with this layer. Okay, so now that we talked a little bit about the concept of deductive reasoning. But by the way, Brandon, do you want to add anything to what I said?
No, I think that's a very clear distinction.
So let us now look for places in our knowledge of mathematics where we encounter deductive reasoning, maybe in some of the things you do at school. It turns out that a lot of times at school, one actually uses inductive reasoning instead of deductive one. And I want to illustrate this to you in the following example. Consider the sequence of numbers. 1, 2, 3, 4, 5. And now I'm going to ask you a question. Which number comes next? What do you think? Okay, I see you're saying 6. Okay, fantastic. So you're saying that it's going to be 6 here, right? Now, this idea that it's going to be 6 here, are you using here inductive reasoning or deductive reasoning? Which one are you using? What do you think? Inductive. Well done. Does everybody agree with that? That it's inductive? We're actually using inductive reasoning here. Fantastic. Now, inductive reasoning is very useful. For example, recognizing patterns is always inductive reasoning. And it's a very useful thing in mathematics. It allows you to discover new things in mathematics. But we should be careful that when we use inductive reasoning, we should be careful not to dismiss other possibilities which seem unlikely, but still it could have been the case. For instance, these numbers could be the number of candies I get from a machine, from a candy machine. So now Tim goes to a candy machine and he feels quite excited because there is this button on the candy machine. And the first time he pressed the button, he got one candy. Second time he pressed the button, he got two candies. So altogether now he has three. The third time he pressed the button, he got three candies. And it went on like this. And now he's expecting that the sixth time he's going to press the button, he's going to get six candies. But guess what happens? He's gonna get zero because the candies have been finished. So with inductive reasoning, he was expecting six here, but in reality, it turned out it was zero. And that's an example how sometimes inductive reasoning can fail you. Okay, so that's good that you understand now the distinction between inductive reasoning and deductive reasoning. Would any one of you be able to give an example of deductive reasoning from the kind of things you learn at school? We had one example where solving an equation seemed like a process of deductive reasoning. Algebraic equations, indeed, yes. Trigonometry. Interesting. So can you give, can you be a bit more concrete? Where in trigonometry do you make use of deductive reasoning? Maybe not all of you have actually done trigonometry because some of you are in grade 8. So let's go back to something that everybody knows, fractions. What is 1/3 plus 1/2? Do you know how to add these two fractions? Find the lowest common divisor, okay, LCD. Is it lowest common divisor or multiple? Isn't it LCM, or am I confusing something here? Denominator. Okay, great. Yeah, thanks. Yeah, so that would be 6, right? So we can rewrite 1/3 as 2/6, and we can rewrite 1/2 as 3/6, and then we can add them, we get 5/6. Is this example of deductive reasoning or inductive reasoning? I think I agree with you. It is deductive. We can, but in order to guarantee 100% truthfulness, we will have to now do this step by step and ensure that at each step we do something that we're 100% sure of. So the first step, let's look at this equality. This equality relies on the fact that 1/3 equals 2/6, and also on the fact that 1/2 equals 3/6. So we would have to be 100% sure of these equalities. Are we? How do we know that 1/3 equals 2/6? So is the fact that 1/3 equals 2/6, is that inductive or deductive? Well, we said originally everything was deductive, so it should be deductive maybe. But then how would you explain? How can you be 100% sure that 1/3 equals 2/6? Some of you are actually saying it could be inductive. That's interesting, because if that step is inductive, then the whole thing will be inductive, right? If in a series of steps, one of them isn't 100% sure anymore, then the whole thing can't be 100% sure anymore. Something interesting happened here. We wanted to explain why this equality is true, the first one, right? We still also will need also to explain the second equality, of course, but let's first talk about the first one. We want to explain the first equality, and we came to a set of two equalities which require explanation before we can explain the other one. So when you want to explain something, right? When you got something and you ask why, it kind of takes you to the more basic level. And then you might want to ask why there as well. So, I mean, this equality, let me reverse my arrow here as well. This equality here is because of these two equalities, right? So the answer to the why question here, why do we have this equality? The answer is because we have these two equalities. But now we want to ask why question on these two equalities. How do we know that they're equal? Why is 1/3 equal to 2/6? So we ask another why question. It takes us to a more fundamental level. And this way one could actually go on and keep asking why questions. But of course, one cannot ask why questions infinitely many times, right? One will have to stop somewhere. So by asking these why questions, that we will hit a place after which we don't ask any more why questions. We're going to talk about this shortly, but let me first see what we have on the chat. I thought something was written there, but now it's gone. Brandon, do you see anything on your chat about?
I think it was edited.
Oh, okay. So how do we know that 1/3 equals 2/6? Would anybody like to answer that? Multiply. Okay, thank you. So we take 1/3 and we multiply the top by 2, and we also multiply the bottom by 2. But now, how do we know that we can do that? So let's ask a why question. So the answer to this why question is kind of this one. But now, how do we know we can do that? And the way we can explain this is we can say, okay, 1/3 definitely equals 1/3 times 1, because anything times 1 is the same thing, right? But then 1 itself equals 2/2, right? And that's how we get the answer to the other, because then this becomes then equal to 1 times 2 and 3 times 2. But we could ask again some of the why questions here. For example, why is it that 1 equals 2/2? And eventually, we will hit this ground that I was talking earlier. And this ground will be the basic rules out of which we derive all the calculations. In mathematics, they're called axioms. So axioms are basic rules which we use to prove deductive arguments are 100% valid. You agree with me, right? If I continue asking these why questions, eventually the answer will be because that's a math rule. You agree with me on that, don't you? Should I repeat my question? I'm asking whether you agree with me or not, that if we ask this chain of why questions like we did here, why this, why that, and then we explain something using something else, and then we ask on that, okay, but how do we know that is true? Eventually, we will hit the ground, which will be the basic math rules. So now we see a very interesting feature here. These axioms, these ground rules, we don't ask why on those ones anymore. We just say we accept them to be true. We believe them to be true. So basically, in some way, they are inductive, maybe. But this can't be. It would ruin the whole story, right? So what actually happens there is that we're not really kind of claiming that these basic rules are true. We are saying if they were true, then our deductive arguments would be 100% valid. So the precision in mathematics, the precision of deductive argument in mathematics is not about absolute 100% truth, but rather about distilling, or maybe I'll use a simpler word there, about uncovering basic rules, which are called axioms, from which other conclusions can be proved with 100% certainty. Does this paragraph make sense to you? Axioms are neither inductive nor deductive. Axioms are things we use as, you can think of them as assumptions. We're saying, we're not asking whether the axioms are true or not. We're saying, based on these axioms, we can establish some conclusions for sure. So if later on the axiom turns out to be true, then we know that our conclusion is true. If it turns out to be false, we don't know anything. We're not making a claim about the axioms, whether they're true or not. We're kind of accepting them, kind of imagining if they were true, and then we're seeing what conclusions we could have drawn from them if those axioms were true. Does that make sense?
Inductive arguments can still use axioms. So
sure, but inductive arguments can use axioms, but they also, but then they're no longer 100% correct conclusions from the axioms.
Yes. So here's a sort of real world example. So when you travel, wherever you go in the world, there's a symbol that the world uses for airports. It looks like a little aeroplane.
Mm-hmm.
And if you're trying to find the airport, because you have to get onto a flight.
So now Tim is traveling.
Tim is traveling, and he wants to find the airport, but he's in a country where he can't speak the language.
Mm-hmm.
So he looks up and he sees a sign and he sees the symbol.
Mm-hmm.
Now, as a general axiom, that in the world, people recognize the symbol to mean that should take you to an airport.
Right.
But Tim doesn't know, perhaps, that maybe that road is closed today and it doesn't actually go to the airport. He can't ask all the necessary questions for that route to take him to the airport. But inductively, it should. He knows that this symbol means an airport. He knows this is a road. So it's a reasonable conclusion that if he follows it, he'll get to the airport.
Right. Maybe there was a tornado. Maybe there's a tornado which makes impossible to cross the road, about which Tim doesn't know. Great. I think this kind of brings us to the end of our session. You probably have other plans. I'm talking about to the learners attending. We were supposed to finish it. We did start much later because of this misunderstanding we spoke of, but probably we should finish on time in light of your schedules. Any questions from your side before we say goodbye to each other? Maybe I'll just make a short summary of what we did today. So the point of today's session was to discuss a very important concept in mathematics, which is deductive reasoning, and to learn how to distinguish deductive reasoning from inductive reasoning, where deductive reasoning is something that relies on 100% certainty, whereas inductive has some component of guessing in it. And then we looked at some examples of this concept, and also at the end we uncovered that even in deductive reasoning there are some components, the so-called basic rules, the axioms, that are part of our arguments. And those axioms, we don't question whether they're true or not. We just accept them to be true, but we're aware of the fact that they could have been false, which would ruin our conclusions. But with the assumption that they're true, then the rest of our deductive argument will be 100% true. Now I'm going to answer the questions that you're asking in the chat. So these abstract algebra sessions are not for covering the KEPS curriculum. For that, there are separate lectures. You will see advertisement of those lectures, the same place where you saw this one. In terms of the next session, the original plan was to have it on Monday. So we will then stick to this plan since you're here today. We thought that you will not be here today. So since you're here, we will stick to that plan. And so the next session will be on Monday. I think it's the same time, if I'm not mistaken. It would have been wherever you saw the advertisement for this session, you would see it there as well, the time for the next session. Yes, so there will be one on Monday, and after that there will be a big break before the next one. But meanwhile, you can after Monday's session, you can go back and watch those videos I showed you at the beginning. It's altogether a total of 8 hours of discussions. Okay, so we will then end off here. Thank you very much for joining and for your participation.
Thank you, everyone.
Yeah, thank you. I'm very glad to hear that you found it interesting. It was very interesting to interact with you. And thank you, Brandon, for joining us from all the way from Netherlands.
Happy to be here.
Bye, everyone.